I'm going to present this study using inductive conformal martingales for addressing concept drift in data stream classification. Here is our outline. We say some words about our motivation, some words about the concept drift, about the inductive conformal martingales and the small modification we made, the betting function we used. Then we show our experience results and our conclusions. Our motivation is for this study is because concept drift changes the data distribution. Thus, we have a reduction in models accuracy. Thus, if we found the point which the data changes, we will retrain our model and we will regain our accuracy. Also, the algorithm must be able to handle multidimensional data and adapt to any distribution of p-values, and also should be computational efficient because we have huge amounts of data. We have concept, as we said before, we have concept drift when the data generally distribution changes over time. Here we have a change in timestamp t+1. Recall that the joint distribution of x and y can be given of this product, of this condition probability with this. Thus, if this condition probability is different at timestamp t+1 is different from this conditional probability at timestamp t, we might have a concept drift, or either our distribution of the labels it changes, or if we have combination of those two. If the first one happens, then we have a change in the decision boundaries. But if the second happens, we don't have a change in the decision boundaries. When concept drift occurs, we have pure data predictions. So there is the need for a tool to detect the concept drift as close as possible to the point at which the distribution changes, and then return our prediction algorithm. We have four categories of concept drift. The first one is the sudden drift, where the data generating mechanism changes instantly. Then we have the gradual drift, where the data distribution is replaced with a new one over time. Here we experience, when the drift starts, we experience fewer examples belonging from the initial distribution and more from the new distribution. Then the initial distribution stops is eliminated. Then after that we have the incremental drift, where the new data generating mechanism incrementally replaces the mechanism. Here, each example, each instance is generated by a mixture of distribution, the initial distribution, the final, but over time, the impact of the initial distribution disappears. Also, we have the reoccurring drift, when the previously seen data distribution again reappears. Here we have in gradual illustration. As you can see here, the concept data distribution changes instantly. Here we have points that belong to the red distributions and to the blue one, but over time the red one replaces the blue one. This holds for the gradual drift. For the incremental drift, the examples are generated, or the instances are generated by a mixture of those of the blue and the red distribution, but over time the impact of the red distribution is eliminated. This is more difficult to detect it. And also we have the occurring concept drifts. As you can see here, the blue distribution repeats again, reoccurs again. Our approach will be based on the exchangeability assumption. We will have some random variables zi. Then their joint distribution is exchangeable if it is invariant under any permutation of these random variables. Also, testing if the data is exchangeable is equivalent to testing the data for being IID. A test exchangeability Martingale is a sequence of random variables that are greater or equal to 0, and also they keep the conditional, this conditional expectation here. To show how Martingale works, consider a fair game where a gambler within infinite wealth follows a strategy which is based on the distribution of the events in the hidden game. The gain of this gambler, the gain acquired from this gambler can be described by the value of a Martingale. Specifically, variance inequality indicates that the probability to have high profit is very low. As C increases, this probability, the bounds of this probability decrease. Here we have let Zi is a sequence of examples. Xi is the feature vector and yi is the label. The first k examples will be used to train our underlying algorithm. Then the examples will arrive one by one. The numerical value called non-conformity score will be assigned to each example. The non-conformity score is based on our underlying algorithm. And when a new example arrives, a new non-conformity score is assigned to each example. Our underlying algorithm is the simple tree classifier. The non-conformity score is based on the posterior probability of the underlying algorithm, is the opposite of this posterior probability. Here we calculate, is the formula for calculating the p-values. We have a sequence of non-conformity. In these brackets here, it's the number of elements in Hj that are stranger than Aj, the current example. And here we have the number of elements which are equal to Aj, that have the same strangeness, multiplied by a random number belonging to 0, 1, and divided by the total number of elements in this sequence. Now, a conformal Martingale, which is an exchangeability Martingale, which is calculated as a function of p-values, is this product where Fi is the density estimator, which is used as a Betty function. Fi is calculated with the help of the previously seen p-values, and we have applied a new def on the new p-value of the current example. Also, it can be written in this recursive way. As before, the exchangeability assumption is rejected if at the significance level 1 over m, if the value of Sn is equal to m. This is according to the Pvalue's inequality. The betting function we have used here is the histogram betting function, histogram estimator, histogram density estimator. It's very simple to find it and also very computationally efficient. To calculate the histogram betting function, we just have to partition the interval 0 to 1 into k sub-intervals according to your number of bins. Then you count how many p-values belong in each interval. And when you want to apply this f on the new p-value, we follow this formula where kappa here, K Greek kappa here is the number of beams, and J is the number of p-values that belong to these intervals here, to the interval Bj, and divided by the number of observations. No, number of observations, yes. To detect concept drift with inductive conformal martingales, first we have to calculate our nonconformity score. Then we calculate the p-values. After that, we calculate the estimator, and we apply this recursive formula for calculating the value of the martingale. If the value of the martingale is greater than 1 over delta, then we raise an alarm and we have a concept drift detection, and we have to retrain our algorithm to gain accuracy. For example, if we have that the value of Si is equal to 10 or 100, then we can reject the exchangeability assumption at a significant level equal to 10% and 1% respectively. Here we have a modified version. This modified version is very simple. It's same as before. We just here restrict the lower value of the martingale with epsilon, because when the data is exchangeable, the value of the martingales becomes very slow, very near to 0. Again, it works like this one. Unfortunately, here we might have a potential loss in theoretical validity, but our experiments show that it's still practical. Here we show a comparison of the histogram Bethe function with the kernel. Although the kernel might perform better if it is well tuned, unfortunately it's very slow, at least on my machine here. For this reason, we choose the histogram Bethe function. As we can see here, we have generated n p-values. At 10,000 p-values, the histogram needs 6 seconds, while the kernel needs 56. At 100,000 p-values, the histogram needs about 2 minutes. The kernel needs about 9 minutes. The hardware we use is a CPU Ryzen 7 5800X with 32 GB RAM. The number of units we used is 22 for the histogram, which is the maximum which we used in this study. Also, the study visual size for histogram and kernel density estimator is 10,000, and 100 for the histogram is 10,000, for the kernel is 100. Here we describe our data sets. The study consists of about 1 million instances. We have 3 variables, which each one takes 3 values. It's a binary problem. Number of concepts equals to 4. We have 4 distributions here. The chunk size is 10,000. In each chunk we have 1 distribution, and the training set size is 3, because we have 3 categorical variables with 3 values, and it's a binary problem is sufficient enough to have good accuracy. The C dataset consists of 400,000 instances. It has 3 numeric variables with values from 0 to 10. The number of labels is 2. The number of constants is 4. Again, 4 distributions. The chunk size is 100,000, and the training set size is, we set it to 1,000. And here those 2 are simulated data. The electricity data set is a real world data. It has about 45,000 instances. We have 8 numeric variables. is a binary problem. We don't know the number of concepts because the real data set. We don't know the chunk size, but we set the training set size to 300, and it performs really well, fairly well. For the C dataset, the left dataset, we have performed 30 simulations, while for the stacker only one because we have a big number of instances. For experiments we use for algorithm one delta 10 and 100. For the algorithm is the inductive conformal Martingale. The algorithm 2 is the modified Martingale with delta equal to 10 or 100 and epsilon equal to 0.1 as 0.01. For those algorithms, we have applied different values of the number of histograms kappa in the Betty function, and these are 3, 4, 5, and G to C, where G to C means that as the number of observations arrive increases, we also increase the number of histograms. When we have about 20 observations, we take two bins. When we have about 20 to 50, we take a number of bins about 3, and when we have about 50 to 100, we take a number of bins to 4, and this has a maximum value of 22. Our performance measures are accuracy, average accuracy of the predictive classifier. Also, we exclude the training set, the mean delay, the average number of observations needed to detect a causal drift after it occurs, the portion of true alarm, the average portion of causal drifts that have been correctly detected per chunk, the portion of false alarm, which is the average portion that algorithms 1 and 2 erroneously detected a change when no causal drift is present per chunk. And on the real life data set, we use only the accuracy as defined here and the number of causal drifts detected. Here are the results for the staggered data set. Algorithm 1 again is the inductive conformal Martingale. What we can see here is that as delta increases, also the portion of false alarm decreases. As delta increases, the mean delay increases. The accuracy, we also expect that the accuracy should be lower because the mean delay is bigger, but because we rounded our result to 2 decimals, we can't see this. When we said when a drift occurs, the inductive conformal Martingale was able to find it at all cases. Here, when we set the number of bins to GI, the variable number of bins as observations arrive, we have a small increase in accuracy for both noisy data and noiseless. For code here, we injected 10% noise to our data, and here is without noise. Again, with noise and without noise, we have a small increase in accuracy and also a drop in the mean delay. But unfortunately, we have a small increase in false alarms. But still, when we set delta equal to 100, the algorithm is still practical. Here, again, staggered data set. Typo here. Algorithm 2. We
5 minutes left.
5 minutes left with 0.1. When delta increases, the portion of false alarms decrease. When delta increases, the mean delay increases. When we set to GI, we have that an increase in accuracy, and and decrease to mean delay. When we set delta equals to 0.01, we have an increase, we have a small decrease in accuracy compared to the previous one, but still better than the initial, than the first algorithm in terms of accuracy and mean delay. The best results are obtained when we set the number of beans equals to G. Here we show a graphical illustration about the Martingale growth for the staggered data set. As we can see here, we train our algorithm. Then we try to find the cost drift. The cost drift is detected here. Then again, we try to find cost drift, but it's very low here. A cost drift is detected here, and so on. As you can see here, the Martingale takes very small values. Thus, we restricted its lowest value to 0.1, and here is 0.1. This accelerates the process of the Martingale to find the cost drift. The idea here is to find a good density estimator that will be equal to the uniform distribution, but unfortunately the histogram does not manage to do this. I have how many minutes I have? Anyway, here the same holds for the C dataset. As delta increases, the portion of false alarm decreases. Also, as delta increases, the mean delay increases. The best results are obtained when we set the number of beans equals to G. Here, when we restrict the lowest value of the Martingale to 0.1, we have a small, somehow a small increase in accuracy, but we can't see this because we rounded our results to decimals. Also, the mean delay is reduced. The portion of tolerance is 1. It's better than this one before. The portion of false alarms, unfortunately, increases. The same holds here. This is better than the inductive conformal Martingale, but worse than the previous one, because the lower value of the Martingale is 0.01. Thus, it is more slow to go to reach a value of 100. Again, here we have the Martingale growth. The Martingale decreases. Here it decreases. As you can see here, it's a very low value. For this reason, again, we restricted it to take a lower value of 0.1 and here 0.01. Thus, we accelerate the process of detecting cost drift. And here we have the real data set. The best results are obtained when we set the number of beans equals to G. We have an increase of accuracy here when delta equals to 10. When we use the second algorithm with epsilon equals to 0.1, we have again an increase in accuracy almost in every number of beans. And also an increase in the number of courses detected. Some of them might be false alarm, but the results are better. When we set epsilon equal to 0.01, accuracy is improved compared with the first one. The best results are obtained when we set the number of beans equals to G. Again, here is the Martingale growth for delta equals to 100. We consider cases that the Martingale is very low, value of the Martingale is very low, so we restricted it, and we managed to accelerate the process of detecting the cost drift. Here is the detector, we retrain, etc. So we have examined the use of inductive conformal Martingale and the slightly modified version of inductive conformal martingale, combined with a histogram betting function to examine their practicability on detecting cost drift. The modified version improves accuracy and reduces the time needed to detect cost drift. An increase in parameter delta can reduce the portion of false alarms, and an increase in parameter epsilon can help the modified martingale to recover from a low value. The required amount of time is significantly reduced when the number of beans increases as observations arrive. There's a future where we intend to find a more advanced density estimator, use other underlying algorithms, and more datasets. Thank you.